Hey there guys. Today this video is going to go through and explain what a limiting reactant is, what is an excess reactant, and also talking about percent composition. Last time we talked about stoichiometry. Stoichiometry is how you go from moles of a reactant to moles of a product, or moles of a product to moles of the reactant. There's lots of ways that you can use stoichiometry. Before, we were really just looking at if we have one reactant and the other reactant is in excess. There's just a near unlimited amount of reactant B and just a little bit of reactant A. What's the stoichiometry there? But in reality, sometimes you don't have that. So again, if we go back to this sandwich bread example here, we don't have an excess amount of bread. We only have 28 slices, and we have 11 slices of cheese. Pretty quickly, though, you can realize we're going to run out of cheese before we run out of bread. So, cheese in this case is our limiting reactant. Cheese is going to run out first. We are limited in this reaction by the amount of cheese. So that's what a limiting reactant is. This is going to be your excess reactant. How much reactant is left over after the reaction takes place. All right, so that's kind of the terms we're going to be looking for. Limiting reactant is which one of these two is going to run out first. And then an excess reactant is the amount that's left over. All right, so let's kind of go through and see what's happening here. So in this problem, we have iron plus water goes to iron oxide and hydrogen gas. All right, great. So here we have 36 grams of H2O and 67 grams of iron, and they're mixed together. Then we want to know what's the limiting reactant, how many moles of hydrogen gas is produced, and how much iron oxide is produced. All right, so how do we go about this? How do we know which one of these is going to run out of first? Are we going to run out of water first, or are we going to run out of the iron first? How do we know this? All right, so there's going to be two ways of doing it. Depending on how your mind works, one of these ways is going to be better than the others. So the first thing you're going to do for both of these, just like any stoic problem, you have to get things to moles. So that's step one. Switch everything to moles. After that, you can just go through and find the number of moles of a product using each of the reactants. Okay, so basically just go through and do a stoichiometry step. It doesn't really matter which product you choose. Do whichever one makes the stoic problem the easiest. So you kind of have to go through and do two stoic problems here. And then the reactant that gives you the least number of moles is your limiting reactant. All right, let me kind of just walk through with the bread example here. So in this case, what we're going to do, now these guys are in moles, right? They're numbers. They're not weight. I'm not talking about, this isn't 3 ounces of cheese. This is 11 slices of cheese. What we can do is go through and see how many sandwiches can I make with 28 slices of bread. 28 slices of bread, I know can make 14 sandwiches. Okay, if I had an unlimited amount of cheese, I can make 14 sandwiches with 28 slices of bread. Here, I know I can make 11 slices if I had an unlimited amount of bread, an excess amount of bread. Which one of these two are lower? Whenever I do it with the cheese, so this guy is going to be my limiting reactant. Okay, so that's one method of doing it. Okay, let's go through and use that method here. Okay. So first off, let's get these into moles. We have 36 grams of H2O. We need to get this into moles, and so that means moles are on top, grams are on bottom. H2O is 18 grams per 1 mole. I know that just because I use water a lot. So 36 divided by 18 is 2. We have 2 moles of water. And for iron, we have 67 grams of iron. We need to get to moles of iron. Let me go through and look at periodic table. Iron is 55.8. So, same thing here, grams, 55.8. All right, so this one's a little bit, I can't do a quick math in my head. So let me just kind of run through this real quick. About 1.2. 1.2 moles of iron. All right, so let's kind of run through this real quick. If I wanted to do the stoichiometry to go to the iron oxide, right? That means that to go from moles of water to moles of iron oxide, water is going to be on bottom, divided by 4, and iron oxide is going to be on top, and that's going to be 1. So 2 divided by 4 is what? 0.5 moles. Okay, so let's do the same thing here, but with 1.2 moles of this. This case, I'm going to be dividing it by 3 when I do my stoichiometry step. And 1.2 divided by 3, just to make sure that I'm not doing anything weird. 0.4 moles. All right, so 0.4 moles. This is the smaller amount, which means the iron oxide, or the iron, is going to be our limiting reactant. Okay. Iron. Okay. So let me go through and show you a different way of doing this. This way is a little bit faster. You still have to go through and get the moles of these things, but instead of going through and doing a stoichiometry problem, sometimes you won't get something with a 1, and the stoichiometry problem is going to be a little bit confusing. What we can do, though, is just divide the moles of the reactant by its coefficient, just like what we did here. It's just like a stoichiometry problem, but instead of going through and trying to figure out, do I use iron oxide or what was the other thing, or hydrogen gas, or something like that. One thing you can do is just, once you have the number of moles of water, divide it by its coefficient. And then iron, divide it by its coefficient. And whichever one gets you the smallest number, that is going to be your limiting reactant. That's going to be the limiting reactant. That's what you're going to be using going forward with stoichiometry. Okay. There's that. There's going to be a couple of different types of problems you can do with that now. One thing that I could ask you is, how much water will be left over once this reaction goes to completion? Once this reaction is 100% done, how much water is going to be left over? Ooh, okay. So what do we know with that? How do we figure that out? Well, we know that all of this limiting reactant is going to get used up. if we're talking about sandwiches, we know that all 11 slices are going to get used up. But we're going to have some amount of bread left over. In the sandwich example, it's pretty easy. There's going to be 6 slices of bread. This is a little bit more complicated, a little bit harder to think about how much water is going to be left over. So what we can do is, first off, remember it was 2 moles of H2O and 1.2 moles of iron, right? All right. So I know all of this iron is going to get used up. What I want to know is do a stoichiometry problem of how much water H2O is going to get used up if I use up 1.2 moles of iron. So let's just go through and do that stoich problem real quick. So 1.2 moles of iron. There's we want to get 2 moles of H2O. We know iron is going to go on bottom. H2O is going to go on top. We have 4. We have 3. And now just go through and do this problem. Again, since I never trust myself, I want to use a calculator. Times 4 divided by 3, 1.6. So we have used up 1.6 moles of water. We started with 2 moles, so that means 2 minus 1.6 is 0.4. There's going to be 0.4 moles of water left over from this reaction. The rest of the water, that 1.6 moles of the water was used up. So there's only 0.4 moles left over. So we have 0.4 moles of excess water left over. All right. We good there? Okay. So we have that. Now, one other thing is percent yield. I said before about this reaction going to completion, going 100%. Most reactions don't do that. You know, in the real world, everything doesn't work out perfectly. You don't have 100% efficiency in everything. There's going to be some things that just don't react. So that means even though we're doing stoichiometry, and most of the time we're going to get pretty close, sometimes when we actually put it into practice, we're going to have less reactant than we think. So if we have less reactant than we think, we need to somehow quantify that. And that's called a percent yield. So if you have less than 100%, you know your reaction didn't go to completion. You lost some product along the way. Maybe whenever you were weighing the product, you dropped it a little bit on the ground, or you didn't scrape it all out of the beaker, or something like that. Sometimes you might have more than 100% product, and this is something that is kind of concerning, because this means that you have something else in your sample, a contaminant, or what's called a side product, something you didn't expect to happen, a reaction that you weren't expecting to happen had gone off as well. In other words, you got more product than you think you should have. So those are your two things, and it's pretty easy. You just take the number of moles that you measured, and then divide it by what you should have gotten, your calculated stoichiometry, and then multiply it by 100. It's a pretty simple percent problem. All right. So here we go. This is pretty easy. You have all of this stuff. You know that you have 92.6 grams of iron oxide calculated. This is what you should have gotten. But whenever you actually do the experiment, or actually go through the reaction, and you weigh the product, you only get 89.9 grams. Okay, so something's amiss there. What's the percent yield? It's pretty easy. 89.9 divided by 92.6 times 100, 97% efficiency, 97% yield. That's pretty good, actually. In most scenarios, 70% yield, 80% yield is considered pretty good. And for a bunch of high school students, if we were doing a lab, I would ask you to find the percent yield. And quite honestly, if you got 50 to 60% yield, that's a success. That's great. Good job. There are some reactions that are very efficient, some that are less efficient. And in fact, if you are interested in being like a chemical engineer or something like that, a good portion of your job is going to be figuring out how to get as close to 100% yield as possible. So trying to figure out just the right conditions in order to get that percent yield as high as possible. All right, so what is it that I want you guys to actually do? Well, another one of these chem quizzes. It's not going to be 60 or 50 or anything like that. It's going to be the same one, stoichiometry and limiting reaction. I'm going to have an assignment put up for this. I only want you guys to do 10, okay? 10 limiting reagents. But I also want you to include percent yield. So you're going to go ahead and start this. And some of these are going to be percent yields. Some of these are going to be the limiting reactant. Okay. But I just want you to do a total of 10. Or I should say a total of 10 correct answers. So, again, what you're going to have to do is convert. They give you 2 of these. So, for example, this first one, you have a certain number of grams of nitrogen, a certain number of grams of hydrogen. You need to go through and figure out, is it nitrogen or hydrogen, which is your limiting reactant? Once you've done that, do the stoichiometry with a limiting reactant, convert it back to grams, and then figure out your percent yield by taking your measured, dividing it by your calculated, multiply it by 100. All right, so there's several steps there, but here I'll show you. It's not terrible. So you gotta remember nitrogen. N2 is going to be 28, right? So 28 grams per mole. So that means for the number of moles of nitrogen, we're going to have 295.25 divided by 28, about 10.5. Let me write that down. 10.5 moles of nitrogen. And then for H2, 22.17 divided by 2 is 11.0 moles of H2. All right, and then to figure out which one of these guys is going to be your limiting reactant, I like using the just divide by the coefficient rule. So divide this by 3, and then divide this by 1. You can kind of tell already. I mean, 10 divided by 1, 11 divided by 3, which one's going to be smaller? Hydrogen. So this guy is going to be your limiting reactant. And the cool thing is that we already have converted it to moles. We've already converted this to moles. So we can just use this to go forward. Except I'm really messy with this. So let me just kind of clean up. So 11.0 moles of H2. H2 is going to be on bottom, and ammonia is going to be on top. Looking at my balanced reaction, we know it's going to be 2 and 3, which means that 11 times 2, so 22 divided by 3, it's about 70? Or 7 moles? 7.3? There we go. 7.3 moles of ammonia. So this is going to be, what, 14 plus 3, 17? So to go from, move you over here. Now we need to convert this back to grams. Grams to mole. And so it's going to, looking at the molar mass of ammonia, it's going to be, what was it again? 14? 14 plus 3, 17. 17 grams per mole. Moles cancel. So 7.3 times 17 is 124.1. 124.1. So this is going to be our calculated one. Then we take what was actually produced and see what we get there. So 67.12 divided by 124.1 equals, it's going to be about 54%. 54.1%. All right, let's check it out. 54.1%. All right, did I get it right? It's going. Grade it. Grade it. I'm going to take the fact that this website is chugging along as you guys are just slamming the server really hard. That's what I'm assuming. Yeah. All right. Well, I don't know if that's correct or not. I assume it's correct. All right. That is basically how you would go about doing one of these problems. Again, for this, I'm only wanting you to do a total of 10, but mix it up. So that means, so a total of 10, still balanced, do limiting. I want it to be grams, and I want you to include percent yield. Okay? That is going to be your assignment for tomorrow. All right, guys. That's that. Hopefully you guys are doing well. I'll see you guys on Thursday.